Okay, so in this lecture I want to discuss something called linear classification in generality. We're going to relate it to the Bayes classifier we discussed previously, but we'll see that it's a more general framework for doing classification. So this lecture focuses on binary classification. So a binary classification problem looks like this. So specifically for this lecture, we'll assume that our covariates are in Rd. And we're going to assume that with each covariate is associated a label, plus or minus 1, depending on whether that point comes from class +1 or class -1. So we're assuming the plus or minus 1, not 1 or 0 for this problem. And we're going to define a classifier f to be one which makes predictions of the label yi given an input xi and some parameters theta. So in other words, the function f takes in an x, takes in its parameters, and then maps that to an output that's either +1 or -1, which we hope to be accurate in assigning the input to the correct class. Last lecture we discussed Bayes classification framework. So in that case, theta here was the class prior probabilities and also parameters for a class conditional distribution on x. So in this lecture I want to introduce linear classification in a more general framework and then also connect the two. So let's actually motivate linear classification from the Bayes classifier. So with the Bayes classifier, again, we predict the class for a new x to be the most probable label given the model and given training data. So in the binary case, what we have is we predict x to be class 1 if the likelihood of that x, given it's coming from class 1 times the prior of class 1, is greater than the likelihood of x given it comes from class 0, so I used 0 last lecture, times the prior probability of it coming from class 0. So it's just the most probable label. So we can use simple algebra to rewrite this. We can bring the right-hand side into the denominator of the left-hand side and say we would predict 1 if the ratio of the left and right is greater than 1. Take the log of both sides, and we arrive at something called the log odds. So if the log odds, which is the log of the probability of class 1 divided by the probability of class 0, is greater than 0, then it's more probable that it's class 1. We declare class 1. We declare class 0 if this is less than 0. So what does the log odds actually look like for a particular Bayes classifier? So let's consider a Bayes classifier where the class conditional density is a multivariate Gaussian with a class-specific mean but a shared covariance sigma. So both classes have the covariance sigma, but there's a class-specific mean. If we then write out the log odds, if we actually plug in the values for these distributions and calculate them, we'll see that the log odds is equal to this right-hand term. So it's equal to something that doesn't involve x. So this is a function, but notice that whatever this function equals, it's a constant. It doesn't interact with x at all. So call this constant w0, plus this additional term that does depend on x, which is a dot product between x and this matrix vector product, which is also a vector. Call that vector w. So this is something that you can calculate yourself by actually plugging in these values and verifying this, that the log odds declares class +1 if this is positive, class 0 if this is negative, where we have w0 plus the dot product between x and some vector. Okay, so we can write the decision rule for this particular Bayes classifier in this way. We can think of it like this, that we declare our classifier to be equal to the sign of the dot product between x and some vector w plus some constant w naught. So we calculate x transpose w, add a constant, and then we declare the class to be the sign. So previously it was 0, 1. In this case, we're back to plus or minus 1. And the value for w is calculated in this way, and the value for w naught is calculated in this way. So our Bayes classifier, our decision rule, has this type of a form. And we saw that last time when we plotted the decision rule for a multivariate Gaussian, a two-dimensional Gaussian problem where we had the shared covariance. We saw that indeed the Bayes classifier had a linear decision boundary. So this is actually an example of a very general classification framework, a linear classification framework. So a linear classifier is simply one of this form, where we declare the class of label x to be the sign of the function x transpose w plus some constant w naught. So this would be a binary linear classifier. And the Bayes classifier with the shared covariance that we've been discussing is one specific example where w naught is equal to this and w is equal to that. Okay, so the form of w and w naught is restricted to having to be functions of the class-specific means, the shared covariance, and the class priors. But we might want to think of binary linear classification in more general terms, where we put no restrictions on w and we put no restrictions on w naught. So let's now define a binary linear classifier in this more general framework. So a binary linear classifier is a function of this form. It takes in x, and it predicts the label equal to be the sign of this function of the dot product between x and some regression coefficients w plus some constant w naught, where w is any vector in Rd and w naught is any point in R. So this assumes that there is a property in our data set called linear separability. For this to perform well, our data has to be able to be linearly separable in the space that x lives in. So what does this linear separability mean? So two subsets of Rd, A and B. So A is a set of vectors in Rd, and B is another set of vectors in Rd, are linearly separable if it's possible to find a vector w and a constant w naught such that this function is always positive for any x in set A and always negative for any x in set B. In this case, we say that those two sets are linearly separable. So why this is true depends on our geometric interpretation of what this function is actually doing. So this vector w paired with w naught defines something called an affine hyperplane in Rd. And it's very important to understand what that means geometrically to know why we actually are doing a linear, we are trying to linearly separate these two classes with some sort of a line or hyperplane in Rd.